We're told that we have a triangle inscribed in a circle and that AB is the diameter. So first things first, let's sketch that. Okay, maybe it looks a little bit like this. A, B, and C. And the question says that BC is equal to A, AB is equal to C, and CA will be B. Next, we are told that A squared, B squared, and C squared are three consecutive terms of an arithmetic series. And we're asked to express B and C in terms of A. Okay, I'm just going to write that down. So we've got an arithmetic series, A squared, B squared, C squared. Now, in an arithmetic series, you're adding on a constant difference every time. So we're adding D here, and we're adding D here. To get the difference, you can simply do the second term minus the first term. A bit like if you had 1, 5, 9. Of course, the difference is 4. You can get that by doing 5 minus 1. Or you can get it by doing 9 minus 5. So b squared minus a squared must equal c squared minus b squared. Well, we have a relationship. That's not the end, but it's a good starting point. Next, actually, we have, because this goes through the center, we can use the angle in a semicircle circle theorem. So this implies that angle ACB is equal to 90 degrees. And therefore, a squared plus b squared is equal to c squared. So I can replace c squared by that. I can combine these together. First of all, I can write down that it's 2b squared minus a squared. I've just added the b squared to both sides, will equal a squared plus b squared. And actually that means that 2a squared will equal b squared. So I was asked to write down b in terms of a. Now remember, they're going to be positive, so we can just take the positive root. B is going to be root 2a. Okay, I can decide where what I do next, where I want to substitute this in. So I can substitute it into here. So a squared plus 2a squared must equal c squared, which means c is going to be root 3a, because this gives me 3a squared. I just need to then root it. So I've successfully written b and c in terms of a. Next up, we're asked to verify cot A, cot B, and cot C are consecutive terms of an arithmetic progression. So this was part A. Okay, this diagram will still be useful. And in fact, I'm just going to make a copy of it. Right, first up, cot A. Well, remember, I always remember tan. Tan is opposite over adjacent, A over B, so cot is then the reciprocal of that. It's going to be B over A. cot B is going to be then A over B. And cot C, well, cot C is actually cot 90. C is 90 degrees. Remember, tan is not defined at 90, it goes up to infinity, whereas cot actually is 1 over that, and we get 0. So we just need to bring these together. We're going to get B over A over B, and 0. But we've worked out that B is actually root 2A, the A's cancel, and now we just need to show that there's a common difference. Let me just write out again. So root 2, 1 over root 2, and 0. Well, 1 over root 2 minus root 2 is 1 minus, hold on, putting it over a common denominator of root 2. So I times top and bottom of this one by root 2. It's going to be 1 minus 2 over root 2. It's minus 1 over root 2. And 0 minus 1 over root 2 is the same. Okay, we've shown that cot A, cot B, cot C form an arithmetic series. Nice one. Moving on to part C. We have a slightly different scenario now, an acute angled triangle. And essentially we're being asked to prove the cosine rule. Sorry, the sine rule. Okay, so I can label these however I like. Little p, and then this will be capital P, little q, capital Q, little r, and capital R. Okay, and I want to somehow relate these sides using trigonometry. So I draw a line going down the middle, which is perpendicular to R. So there's a right angle here, and I'll split it into 2 triangles. And I'm going to call this H. So I can write down that sine, sorry, 1 second, sort that out. Sine Q is opposite over hypotenuse, H over P. That means H is equal to P sine Q. And then I can write down that sine capital P is H over little q, because it's the opposite over the hypotenuse. And that means that H is equal to Q sine P. Therefore, P sine capital Q is equal to Q sine capital P, and P divided by sine capital P must equal Q divided by sine capital Q. And by a similar argument or symmetry, this must also equal r over sine r. We could have drawn the line going this way instead, which would have formed a relationship between p and r in exactly the same kind of way. So I feel that that should be sufficient to complete this question. So far we've dealt with the triangle and a circle. It's quite interesting, and now we're looking at this acute angle triangle. We've proven the sine rule, and now we're asked, we're told that p squared, q squared, and r squared are 3 consecutive terms of an arithmetic progression, and asked to use the cosine rule to prove this statement here. So let's go for it. First things first, right, we've got p squared, q squared, and r squared. So in a similar way to before, it must be that q squared minus p squared equals r squared minus q squared, because they are both the common difference. Right, now it makes sense to write down the cosine rule, I think, and start from the right hand side and see if we can simplify down to the left hand side. So cosine rule is a squared equals b squared plus c squared minus 2bc cos a. Let's rearrange that to make cos a the subject. So that involves doing a squared minus b squared minus c squared all over minus 2bc. To get rid of that minus, we can just swap the signs around up here. So b squared plus c squared minus a squared over 2bc. Hence, here we go. We've got cos p over little p plus cos capital R over little r. And now we can just carefully replace the cos p by its relevant thing. So it's going to be p squared minus q squared minus r squared. Hold on, I'm using the wrong version now, sorry. Okay, I want to use this one. So it's going to be q squared plus r squared minus little p squared all over 2qr, but I'm also dividing by p. And then for cos capital R, it's going to be q squared plus p squared minus r squared all over 2. Now the BC in this case will be QP. I also want to divide by R. We have a common denominator, so I'm going to get q squared plus r squared minus p squared plus q squared plus p squared minus r squared all over 2qpr. Okay, now do we cancel this down, or do we also write down what this is? And I think that's probably a good idea. 2 cos q over q. Because we've also got these relationships going on that we've not yet used. Sometimes you might be able to see the answer, and if you have already, fair play, taking a little bit longer. So this is going to equal r squared plus, 2 lots of r squared plus p squared minus q squared all over 2 rp, but then I'm also divided by q. Now I'm tempted, actually, I wasn't going to do it, but yeah, I'm going to cancel these out. So actually I'm going to be left with q squared over qpr, because I've got two lots of q squared, that's going to cancel with that too. Okay, and then let's see if we can cancel this down to the same thing. So this is going to cancel, and then how can I use this result? So 2q squared is going to equal r squared plus p squared. So actually this is going to be also be q squared over rpq. And yeah, it's it's not always easy to go from to get back from this back to this. We could have done it, but sometimes it just makes sense to show that the left hand side and the right hand side are the same thing. So these are equal, hence I've already forgotten what we're trying to prove. Cos capital P over little p, cos capital R over little r is equal to 2 cos capital Q over little q. And we proved this using the cosine rule and the knowledge we had on the arithmetic series. Looking at the final part now, we've proven the sine rule and we've got this result using the cosine rule. It says using the results given, prove that cot P, cot Q, and cot R are consecutive terms in an arithmetic progression. So if this is true, then we can show that the common difference is equal. So show that cot Q minus cot P is very similar to before, is equal to cot R minus cot Q, i.e. 2 cot Q equals cot P plus cot R. That's what we're aiming to show. Now we have a relationship, we have that this is true. And so I can take it actually, and I can take my 2 cos Q over Q, and I could divide by sine Q, because this will give me cot Q, and I'll be on my way. Now I need to divide the others by by sine Q as well. Now we have the cosine rule, remember, and it was that what was it? It was sine Q over Q. I'm writing it now with sine on the top instead of on the bottom. Is sine P over P, which is sine R over R. And therefore, 2 cot Q over Q equals cos P. Now if I can replace sine Q by sine P, I can do that because it's going to be Q sine p over p. And I can replace sine q over here in terms of sine r. It's going to be q sine r over r. This is going to cancel, and this is going to cancel. And then these q's are all going to cancel out. So 2 cot q equals cot p plus cot r as required. Just going to write a conclusion down. Cot p, forgotten the order that was in, cot q cots r form an arithmetic series. There's other ways of doing this last little part. I think this is a really solid method, though. You know, managing just to take the not identity, but the equation that we have, that we formed from if you remember, it was p squared, q squared, and r squared being an arithmetic progression. We used the cosine rule to get to this. Using the sine rule as well led us to this, and therefore we can conclude that we have an arithmetic progression. Nicely done. Well done.